All right, thanks. Hi, everyone. My name is Joel Leja. I'm a grad student at Yale University. My advisor is Peter Van Dockum, and I've done this work in collaboration with Marian Franks at Leiden and Kate Whitaker at NASA Goddard. And yeah, I'm going to talk about how to reconcile the evolution of the stellar mass function with the observed star-forming sequence. And specifically, I want to talk about basically what can we learn about the star-forming sequence from looking at the evolution of the mass function. Okay? And so basically, the mass function and the star-forming sequence both tell us how galaxies build up mass. They're kind of fundamental observables of galaxy evolution. And they're also critical inputs and constraints to models of galaxy evolution. These things are sort of central to main sequence integration, to semi-analytical models, to hydrodynamical simulations, to abundance matching models, and to models that look at galaxy evolution at a constant number density. So these are very important things. And they all tell us stories about how galaxies build up mass. And so it's very important that the stellar mass function and the star-forming sequence tell a sort of consistent story. Okay? And so the stellar mass function and the star-forming sequence, they can be used to put powerful constraints on one another. That's because the first order, they're a sort of derivative integral pair. The stellar mass function grows to first order primarily through star formation. And so people have examined this in the past, and this is a plot from Simona Weinemann's paper in 2012, where she built a sort of very, very simple toy model. And she took the stellar mass function at redshift 0.9, it's the dashed line there, and then she grew the stellar mass function with star formation alone, no correction for quiescent galaxies, no merging, nothing like that. She grew it with the star-forming sequence and showed that basically if you compare the grown stellar mass functions with the observed stellar mass functions at redshift 0, you can use this to put constraints on the slope of the star-forming sequence. And this is important because measurements of the slope of the star-forming sequence have been anywhere between, basically a -1 and 0 in this parameterization, where it's a specific star formation rate. So this is something that we can use to learn about sort of the star formation sequence. Okay? So this was a very simple model, and there's ways that we can improve on it as well. And we can also extend this model to higher redshift to see whether it also holds true at high redshift, because there's been a lot of new observations that have come out since then. And so that's what we do here. We take a fresh look at the consistency between the star formation rate sequence and the stellar mass buildup. And so we do this with two data sets here. We take the stellar mass function from the Z-Forge survey, which also includes Candle's data. This is basically, it's the deepest stellar mass function available right now. It covers between locally all the way out to redshift 3. And one of the most interesting things we've learned about it so far is that there's a lot more low mass galaxies at high redshift than people previously knew. And so here it's, we're comparing survey depth limits to some other surveys of the mass function. And Z-Forge goes quite a bit deeper at redshift 1 to 1.5, as well as higher. And I also use the star-forming sequence measured from Whitaker et al. 2012. Uses NMBS data and measures star formation rates. It's a homogeneous UV plus IR star formation rates. And so we use this combination of star formation rates and stellar mass, and we model their consistency here. Okay? And so we start out with a very, very simple model. Basically, you take the observed mass function here, and then you grow it with the star formation sequence. You have to extrapolate both the mass function and the star formation sequence to low stellar masses. And then you modulate the growth due to star formation by the fraction of star-forming galaxies, assuming that quiescent galaxies form no stars here. And there's also a correction for passive stellar evolution. We approximate this as an instantaneous correction. And then what you can do is you can compare the evolution of the mass function as it is observed to the evolution predicted by the star-forming sequence. Okay? And so we could do that. This is a very simple model. I'm going to show it to you right now with no mergers, starting from redshift 2.25. And so here, this is the black one is the observed, and I'm going to show you a blue one, which is grown with the star-forming sequence. All right. There we go. And so you could see there's immediate problems here. Essentially, the mass function that's grown with the observed star-forming sequence blows up. It grows way too quickly. And so this star-forming sequence extrapolated to low masses, like it can't hold. There must be something wrong here. And so there's three sort of immediate possibilities. One is there's a very high merger rate here, and all these low-mass galaxies are destroyed by mergers or absorbed into larger galaxies before they can make the mass function blow up like this. It's also possible that you could lower the average growth rate by adding a large number of quiescent galaxies at high redshift. And the third possibility is that, okay, we haven't really observed the star-forming sequence down to this mass limit yet. Maybe extrapolating it doesn't quite work. Maybe it has some sort of different behavior at low masses and high redshifts. Okay, so these are the three possibilities. And we can investigate these. And so what we do here is we just go into the Guo et al. 2013 SAM, and we measure the destruction rate of low-mass galaxies. And by destruction rate, I mean if it merges with a larger galaxy, we consider it destroyed. And so you can measure this directly from the semi-analytical model. The destruction rate is moderate. It's about 8-9% per gigayear at redshift 2, and that drops down to about 2 or 3% locally. Okay. You could take this, and you could apply it to the mass function. And so here we assume this happens in 1 to 10 merger ratios. It actually doesn't matter, because as you can see, this sort of modest merger rate, it basically has almost no observable effect at the low mass end of the mass function. These are two lines. There are two distinct lines, but it's barely even observable on this scale. And so basically, the merger rate it's not sufficient to sort of reconcile the star formation sequence and the stellar mass function here. The merger rate is too low. Okay? So merger rate doesn't work. You would have to up the merger rates by about a factor of 100 for that to sort of reconcile the two. Okay? There's also a possibility that there's an undetected population of quiescent low-mass galaxies at high redshift. The Z-force mass functions are complete, nominally down to these numbers, so we should see them in the mass functions. You can assume you didn't, and you would have to miss a factor, the number density of quiescent galaxies would have to increase by about a factor of 1,000 for this to work. And this is something we probably would see at lower redshifts. So we can rule that out as well. The final possibility is that maybe the star-forming sequence behaves differently at low mass. Maybe it's not a single power law. Maybe it has to get steeper at low mass. And so that's what we sort of test out here. And we postulate a new functional form where it has one slope at high masses, a shallow slope, and then a steeper slope at low masses. And so this retains the observed normalization and the observed slope at high mass. But then what you do is you make it much steeper at low masses. And we can test that out as well. And so this is it in green. And as you can see, it's much more stable. It works much better. Here we use a slope of unity for the low mass slope. And so this broadly reconciles the evolution of the mass function and the star formation sequence.
Your beta is what, the SFR?
Yeah, that's a good question. So it can be defined in specific star formation rate, which would be basically you add 1 to the slope in specific star formation rate to get the relationship between star formation rate and stellar mass.
And that's what you're using?
That's what I'm using, yeah.
So your beta of 1 is paying at our beta of 0?
Yes, yes. Yep, and so the reason this new functional form removes the rapid growth of low mass galaxies is because basically if you change the slope, you change the mass doubling time here. And it's a very large factor. If you change the slope from the observed slope in Whittaker et al. Of about 0.44 at redshift 2, you change it to a slope of unity, that's more than an order of magnitude in doubling time we're changing. Okay, so we're drastically changing the growth of low mass galaxies.
So since the mergers don't affect it so much, would that imply that your slope needs to be even stronger, perhaps?
The slope?
Yeah.
Oh, you mean because it still doesn't quite work here? That's an excellent question. And so there's still an offset here. It doesn't quite work. And so there's a number of things that we can tweak. We have a number of knobs that we can tweak in order to make this work. And the problem is it's hard to tell which one is wrong. You could have errors in star formation rates. You could have errors in stellar masses. And almost certainly we do, because if you compare these things between publications, they often don't agree. You can change the merger rate, by a factor of 3, 4. This is also something that's not well constrained observationally. And also our model treatment of mass loss isn't perfect. So I'm not going to go into this too much right now. We delve into this more in the paper. And we try to sort of merge all these things and create a sort of reasonable model. But instead, I'm going to use the last couple of minutes to talk about the implications of having 2 different slopes to the star forming sequence. So first off, okay, I'm saying there's 2 slopes. Has this been observed yet? Is this something that people are seeing? The answer is Not really, kind of. So as of a couple months ago, this is something that had been hinted at in several studies. But it tends to be somewhere like just around the mass completeness limit. Studies need to just go a little bit deeper to be able to sort of confirm this, say yes or no. You know, if this is something that is true, if there are indeed two distinct slopes here, then one thing that's interesting is that measurements of the star forming sequence have derived all kinds of different slopes. And so this is from I know. The error bars are all very small and they're nowhere near each other. This is applied from Spiegel et al. 2014. Basically shows that a lot of people have derived a lot of values for the slope in the star forming sequence. And it's sort of unclear what it is, you know. So one possibility here is that maybe there's two slopes. What's happening is the slope you derive will depend very sensitively on basically how deep you go in stellar mass. The deeper you go, the closer to unity it's going to be.
Does it also depend critically how you deal with the passive objects?
Yes, it does. And so that's part of what this plot is showing here. Yeah. Yeah, so there's a number of dependencies. This would be one among many. Yeah, that's a good point. But anyway, so there hadn't been any observations till recently, but then in a companion paper, Kate Whitaker used candles in 3D HST data to actually go out and explicitly measure this. And she split galaxies at a mass of about 10.2, and she asked, well, what is the slope? And is it different? And it turns out this is what she found. The slope at low masses appears to be close to unity. And the slope at high masses is flatter, and it also evolves with redshift. Okay, so this is something that has been sort of predicted phenomenologically. And also, if you go out and look at real galaxies, it turns out it just might be true. Yeah? So sort of the last question is, how's it work in theoretical models? You know, I've said you need this sort of two-part power slope or power law in order to reproduce the evolution of the mass function. So this must be in place if you reproduce the evolution of the mass function. And it turns out, if you plot these relationships between star formation rate and mass, you take them from hydro models, from abundance matching models, you know, from semi-analytical models, you actually do get this sort of difference in slope at the high mass end, the low mass end. Okay? And people have argued in the past that this difference in slope is something that might be a problem with the models. Maybe it's coupling the star formation rate too closely to the specific dark matter accretion rate. But our work sort of suggests that if you actually want to reproduce the evolution of the mass function, a mass-dependent slope is a critical component of any theoretical model trying to do that. So that's the end. I'll leave up my conclusions. Yes.
We looked at all this analytically.
Yes.
With a rather different approach, but just very briefly, if I may sort of summarize that for people, what we basically did was took as an ansatz that the faint end slope of the star-forming mass function was observed to be constant. We took also as an ansatz that beta was indeed a constant, and then we looked at how much merging we had to have in order to keep alpha constant given that beta. And the summary of that was that the beta of our beta of minus 0.1, which is I think your beta of 0.9, we could do that if the specific, like we characterized merging as the specific mass increase rate due to merging to be compared with the specific star formation rate increase of mass. If that was about a tenth of the SSFR, then we could actually keep alpha exactly constant with a beta of minus 0.1. As beta gets to about minus 0.4, it becomes indeed completely impossible. But that tenth between the specific merger mass rate and the specific star formation rate fits, as far as we could see, extremely well with the sort of observed estimates of merger rate. So we concluded from that merging worked extremely well, and that that was enough, and in fact this sort of merging you see in the sky would have this effect of keeping the faint-end slope nice and constant.
Mm-hmm. Yeah, and so they're consistent, I think, the two works, just because you guys chose a beta of negative 0.1, and so yeah, you can have merging reconcile it if you already have a steep relationship between stellar mass and star formation rate. Yeah, that's definitely true. I guess the question is whether or not you take seriously sort of the less steep slopes, the slopes of, in my parlance, 0.6 or so. And so there's definitely some scatter in the observations. Yeah, and this may be one possibility, one way to get around that.
Did you have another question?
Yeah, about where to change the slope. Would it be possible to change the slope at 10 to the 5 in stellar mass, to 2 in stellar mass, and we will get, I could well imagine that from a bounding matching perspective, you have very many objects that would match this very low stellar mass. Whatever you set your initial.
Well, there's certainly transition somewhere between 10 to the 9.5 and 10 to the 10.5. But our model actually isn't particularly sensitive to the transition mass. So we just chose 10.5 and moved on with it. Kate Whitaker found it was closer to 10.2, and it's unclear where exactly the transition mass is. But actually, this kind of model isn't particularly sensitive to where the transition mass is. So that's not a, that number is not something I think we can approach with this sort of phenomenology.
I kind of disagree. I think it would be around L star, but we can talk about that.
Yeah, well, maybe it's, I think there are other things that we're neglecting in this analysis as well, like.
The key thing, you need a low beta where you're in the power law part of the mass function.
Yes.
Where you're at the exponential cutoff, it's exponentially cutting off, and so you lose much sensitivity to the slope of beta.
Yes, I agree.
Oh, Sandy.
So there's a long-standing problem with little galaxies that they, unless you do something, as the gas falls in, they make too many stars early. And so semi-analytic modelers are looking for solutions to this, putting the gas in some sort of inert reservoir, which I call the parking lot, then to be available for star formation later.
Mm-hmm.
Is that problem really this problem?
I'm not sure. I'd have to think about that for a while. They're trying to slow down star formation?
They're basically trying to slow down star formation, but then recapture gas later.
Yeah, so in this picture, the models sort of have a lower star formation rate than the extrapolated high mass star forming sequence would predict. So I think those might be different problems, but I'm not sure. It's a good question.
The net result is either way, at low masses, you're forming less stars at early time, fewer stars at early time. So I would say that they must have some elements in common, even if they aren't exactly the same.
Well, this is kind of getting observations to match observations. You've got one set of observations, and the problem is they didn't match the other set of observations.
It's differential mass growth. As soon as you don't have constant SSFR, you don't have constant mass doubling time, you'll get
you change the slope.
that, and it's,
Yes.
it's really fast.
Yeah.
What does the local observation tell us? You must have this function much further than we do at high bridges. The lowest mass.
You would have liked to think so, David.
Nope.
I just didn't see it. I was looking for the Z0 when extrapolated went down to 0.5.
Yeah, so it's not quite all the way down to redshift 0. There are some, there's still some wiggle room, I think, even in local studies. So at the very end of this plot, you could see measurements in this compilation have ranged from a slope of 0.3, 0.4 to 1. I think on average, most studies tend to find around 0.7, 0.8. But there is very large variance, even locally, unfortunately.
Consistent with Whitaker's
there's a number of definitional issues here, like what is a quenched galaxy, and are they included in the star-forming main sequence? And also there's a difference between what kind of indicator you use, UV, FIR, all these things will give different answers. Kate Whitaker's extrapolated slope is 0.7 locally at redshift 0. Yeah.
Okay, so thank you, Joel.
And specifically, I want to talk about basically what can we learn about the star-forming sequence from looking at the evolution of the mass function. Right? And so basically, the mass function and the star-forming sequence both tell us how galaxies build up mass. They're kind of fundamental observables of galaxy evolution. And they're also critical inputs and constraints to models of galaxy evolution. These things are sort of central to main sequence integration, to semi-analytical models, to hydrodynamical simulations, to abundance matching goes to first order primarily through star formation. And so people have examined this in the past, and this is a plot from Simona Weinemann's paper in 2012, where she built a sort of very, very simple toy model. And she took the stellar mass function at redshift 0.9, it's the dashed line there, and then she grew the stellar mass function with star formation alone, no correction for quiescent galaxies, no merging, nothing like that. She grew it with the star-forming sequence and showed that basically, if you compare models and to models that look at galaxy evolution at a constant number density, so these are very important things, and they all tell us stories about how galaxies build up mass. And so it's very important that the stellar mass function and the star-forming sequence tell a sort of consistent story. Okay? And so the stellar mass function and the star-forming sequence, they can be used to put powerful constraints on one another. That's because the first order, they're a sort of derivative integral pair. The stellar mass function grows the grown stellar mass functions with the observed stellar mass functions at redshift 0. You can use this to put constraints on the slope of the star-forming sequence. And this is important because measurements of the slope of the star-forming sequence have been anywhere between, basically a -1 and 0 in this parameterization, where it's a specific star formation rate. So this is something that we can use to learn about sort of the star formation. All right, thanks. Hi, everyone. My name is Joel Leja. I'm a grad student at Yale University. My advisor is Peter Van Dockum, and I've done this work in collaboration with Marian Franks at Leiden and Kate Whitaker at NASA Goddard. And I'm going to talk about how to reconcile the evolution of the stellar mass function with the observed star-forming sequence.